Welcome back to our last lesson for this week. In this lection, what? In this lecture, we're going to be talking about a common mistake that students tend to make when we introduce the idea of blocking. And the common mistake is that students want to test the influence of block. So this lesson is going to really focus on defining what a test for blocks would be, and then trying to convince y'all not to do tests for blocks / why we don't test for blocks. Additionally, we're going to introduce a calculation or a statistic called relative efficiency, which is going to at least give us an idea of whether our blocking was effective or efficient or not. Okay, so let's get started on basically asking the question, should we be testing on blocks? So let's say we're going to test blocks. Then we typically have our mean squared error for what we're normally testing. Normally it's the treatments, but in this case, we're going to test the blocks. So we have our MSB divided by our MSE. So it's almost the block signal to noise ratio. And so if we did this, we would have this ANOVA table with our F statistic. To be able to tell you if this is a formal test or not, we could go through a lot of theory, but I'm not going to put y'all through that pain. And so I'm going to try and do this through the expected mean squareds. And we've talked about this in lesson 2 under what I believed was called further insights. And so let's kind of just review what we talked about then and then move on. So remember, when we talk about expected values for an estimator, it's going to tell us on average what would we expect for that estimator if we repeated the data collection over and over and over again. That is its on average true value. That's just a reminder. Okay, so let's talk about the expected mean squares for the treatment. So recall that MST is going to be an estimate. And so an on average, this estimator is going to be a proportion of the background noise as well as a piece of the treatment effect. Okay? Now the MSC, which is an estimate of our variance, is on average would represent the true background noise. So this is the on average, what is our background noise? Okay? Now, if we recall our hypotheses that we're looking at, H naught, alpha of 1 equal to alpha of 2 equal ... equal to alpha of whatever treatment, because we're going to be looking under treatment just right now, equal to 0. So under our null hypotheses, this term, again, is going to equal 0, be really, really close to 0. And so that's going to imply that our MST would just be the square root, or not square root, sigma squared over our MSE. So they're going to be pretty close. And so our F would be pretty close to 1. Okay. Now, under our alternative, we say that at least one of these differs. And so this is going to be greater than 0, which is going to imply, wrong notation, MST is greater than MSE. And so our F is too big. Okay. Now let me repeat that since there was a little mistake. Our alternative says that at least one of these is going to differ. And so this is going to be a positive value. It's going to increase this. So our MST will be greater than our MSE. And so our F stat's going to be too big. Okay, now I want to take this same idea and apply it to blocks. So if we were to apply it to blocks, we'd have the mean squared of blocks is this, and the MSE again is still that. Now notice that the MSB does not have the sigma squared term, and this is because of how we randomize. So under the null, if there was to be one, H naught, beta 1 equal to beta 2 dot 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 beta t or little b equal to 0. If we were to have this, under the null, all these sums would go to 0, but then we would no longer have this f of MSB over MSE approximately 1. It would be 0. And so that doesn't really make sense. And so it's not going to be a valid test for blocking. Now, again, we could go into more theory, but I don't want to throw that at you guys because that's not what this class is about. And so the overall idea, blocking is here to explain variability. Okay, if there wasn't this blocking term, if blocking isn't there, then all the blocking information is going to go into the error term. So, oh, here it is. So if blocking's not here, it's going to go into this error term. All right. Again, we saw a more visual picture of this in lesson 1, I believe, when I was talking about systematic and unsystematic and introducing the idea of blocking. Okay. So again, blocking is there to explain the variability. If the block's not there, then all the block information goes into the error degrees of freedom and sums of squares, which is going to make it bigger. And our goal is to explain more out of the error term so that there's less noise in the data. Okay. The issue is why sometimes students think that shouldn't be there. I don't know why that was there. So the issue on why sometimes students think that they need to test for blocks is because of the software. So R or JUMP or SAS or whatever software you're going to do, it will provide you a p-value for your blocks. This is incorrect. The reason why the software does that is because when you're doing your analysis in software, you don't ever really say, hey, that's a block variable. So we need to be smarter than the computer and not use the f-stat or the p-value. All right. Now, I just told you guys that we can't test for blocks. So you might be like, hey, well, how do I know that blocking was a good idea in this situation? So now we're going to talk about relative efficiency calculation, which will be able to tell us if our block was useful or effective or not. Okay. Now, it's just this is a statistic that is calculated. It is not a formal test, but it is just going to just give us some information on whether the blocking was effective. So how do we assess whether blocking was worthwhile? So this far, when we've talked about blocking, it's been about blocking out extra sources of variability. So it seems maybe the intuition is that we just block everything we possibly can. And there's the thought that this also isn't the best experimental protocol either. So we're on kind of the two big ends. We don't block at all, or we absolutely block every possible thing. Not the best case. And so we're going to kind of talk about like where blocking isn't beneficial. Here's the thing to note though. If we make our design to have blocks. So we set up our design, we set up our study to be a randomized complete block design. We can't just drop the block from the design. So if we design it with blocks, we also have to fit the model and we have to run it as a randomized block design. Overall idea, if you design it with a block, you got to analyze it with a block. So our thought process here is that we're going to compare an estimate precision under the randomized complete block and the complete randomized design. So we're going to compare the estimates with and without blocks. And the whole idea is that if we don't have blocks, we're back to lesson 2 with the completely randomized. All right. So our estimate precisions is a measurement by the variance of the estimated treatment means. So for our RCD, i.e. new block. Our variance is our MSE of our CRD divided by N. And then our variance of the RCBD, this is width blocks, is going to be our MSE over RCBD divided by B. Now here, N and B are acting the same because if we remember about the CRD, this, our Yij, is our ith treatment, and this dot is representing the EU in that. So this is going to be 1 to N, right? So if we were in treatment 1, then we would have 1, 2, 3, 4 replicates, or 1, 2, 3, 5 replicates, and then we would go to treatment 2. And so this little n is showing us our number of treatments, or a number of replicates in this treatment. In our RCBD, our I is the treatment, and our J, which is being summed over here, is the number of blocks. So we're averaging over the blocks. Since in a randomized complete block design, we have 1 replicate per block, we average over those blocks. This little n and this little b are the same. Okay, so the relative efficiency of the RCBD compared to the CRD would be the MSE divided by N is going to be equal to the MSE of RCBD divided by B. Another way we could look at this is through here. And so all it is the ratio of the complete randomized design divided by the randomized complete design. And so when blocking is not effective in a randomized complete block design, then these two MSEs are going to be pretty close to each other, or pretty close to 1. And so our number of replicates is going to be equal to roughly equal to the number of blocks. Now, when blocking is efficient in a randomized complete block design, the MSE for the RCBD is going to be less than the MSE of the CRD. And so our relative efficiency up here is going to be greater than 1. Okay, and so what it's telling us, so as the relative efficiency gets bigger, it's telling us that the number of replicates in a complete randomized design needs to be much larger than the number of blocks if we were to have the same precision. So in order to get the same amount of precision in our RBCD, we're going to have to increase the number of replicates to match. Okay, let me repeat that one more time. If we're in this case, saying N needs to be bigger than B, it's saying we need a lot more replicates in our randomized or complete randomized design to match the amount of precision we have with using just this many blocks. Okay, here's the issue with, while this formula looks great and the whole idea behind it's awesome, our issue is that we didn't carry out a completely randomized design. And again, if we make a study that has blocks, we can't just drop it from our analysis. So we have to do some estimation or approximation and replace our MSE for our CRD by this approximation. And there's some theory that goes behind it, but again, you guys won't have to worry about that theory. Just, this is the approximation. And if I ask you to use it on a test, I'll give you this formula. So don't worry about it. What you'll have to worry about is knowing where to get these estimates from. Okay? And so you'll notice that here's our approximation, and we're using the MSB from the RCBD and the MSE from the RCBD. Okay? Now, if we take this and we plug it into this up here, you'll notice we get this. Now I drop the subscripts, but here, here, and here are from the randomized, ooh, that's a bad C, complete block design, ANOVA table. Okay. Now, again, this is just a rule of thumb that if blocking is efficient if our relative efficiency is greater than 1.25. Again, this is a rule of thumb, and again, this is not a statistical test. Okay. You could also, if you're interested in looking at the proportion of variability removed by the RCBD, you can look at this statistic here. So again, relative efficiency, we have to do some estimation for the MSE of the completely randomized design because we don't carry it out. And this is a rule of thumb. It is not a statistical test. Okay, now let's do an example to hopefully help put this in concrete terms. So here is our insecticide example. We have our treatments, block, error, ANOVA table. To calculate our relative efficiency, we need our number of blocks, our MSB, our number of treatments, and our MSE. Okay, so our MSB is here. Our MSE is here. Don't forget that our degrees of freedom is little b minus 1, and our treatment is little t minus 1. So if you do the math, we get b equal to 4, t equal to 3. Or if you remember our problem was that we were testing 3 insecticides and we had 4 plots or blocks, depending on how you want to call it. Then you just plug it into the formula and you get 9.92. So since our relative efficiency is roughly 9, is greater than 1, we can say, or we can kind of conclude that our block was efficient in reducing the variability in the insecticide experiment. And if we go back to our insecticide experiment, remember our blocks were over, we had plot 1 near a goat, we had plot 4 near some trees, we had plot 3 getting some drainage off of plot 2. And so it kind of makes sense that our blocking was a smart and useful idea in that experiment. You can also have another interpretation of relative efficiency, and so we'll go back, we'll stick with the insecticide experiment. And so to achieve the same precision that we got here with 4 blocks per treatment in the RCBD, we would need 40 replicates per treatment. Okay, and so again, this is just saying that the randomized complete block design was useful because it also saved us a lot of resources. And so if we were to do this with a completely randomized design, we would need 40 replicates per treatment rather than what we had in our original experiment. Okay. Now, the one problem of blocking is the degrees of freedom. Okay, so if we didn't have blocking, these 3 degrees of freedom would come into the error term. Okay, and so we would have 9 degrees of freedom. And if we recall, our MSE is equal to our SSE divided by our degrees of freedom. And so by making this bigger, it's good. By making this bigger, it will make our MSE smaller. I had to be a little bit more clear, specific on what good was. Here's the problem. If we don't have block, then this SSE is also going to come down here. Okay? If there was no block. So the point of a block, or more specifically, when it's useful, is when we can decrease our sums of squared error enough to compensate for the loss of degrees of freedom in the error term. Okay? Let me repeat that one more time. That was a little choppy. Blocking becomes efficient and useful if we can decrease our sums of squared error enough. Here's the thing. If you introduce a block, this will go down. But the question is, did it decrease enough to compensate for the fact that we pulled some degrees of freedom out here? If that's true, then blocking will be effective. So in summary, what we talked about in this lesson was, should we test for blocking? No. So if you see a p-value, if there is a p-value or a statistic there, don't read it. We don't test for blocks, but what we can do is do a relative efficiency calculation to help us provide us information to see if our blocking was efficient or not. The whole idea of relative efficiency is to compare the MSE for a completely randomized design to the MSE of a randomized complete block design. Because we don't have, or because we didn't conduct the completely randomized design, we end up doing an estimation to solve it. Again, the relative efficiency is not a statistical test. It's kind of a rule of thumb thought process. That concludes our lessons for this week. You should be able to do your homework now. If you need help with R or jump, go to those videos. And then I'll see you in office hours or messages on Slack if you need me. Have a great day.